So we're working on lecture number 3. Lecture number 3 is going to be about atoms and elements. If you have a periodic table that you can look at while you're going through this lecture, it'll help you. So the idea of atoms first comes from the ancient Greeks. The ancient Greeks, like Democritus, their idea of the atom was they didn't like the idea that you can cut matter an infinite number of times. They felt like at some point you have to get to a small enough particle, and that particle was atoms. So they had a whole bunch of theories that there was these things called atoms. The way that the atoms combined together gave you different matter, but it was more encompassing that they felt like the soul was made out of matter, dreams were made out of matter, light was made out of matter. Out of atoms. Everything was made out of atoms. So it's not the way that we think about atoms, but it was this idea that there is the smallest particle that matter is made up of, and they are different atoms, and the different types of atoms combined together to give us the different things that we see. So it's similar, but it's really of a philosophical. They weren't doing experiments to come up with this idea of atoms. It was just based off of the philosophy that doing something an infinite number of times, like cutting something infinite number of times, would be impossible. Fast forward like 2,000 years or 3,000 years, and we come up with Dalton's atomic theory, which is now going to be different than the ancient Greeks, and that this is not going to be a philosophical approach. This is going to be based off of experimental evidence. So we're in the 1800s now. This is not actually 100% true, but pretty good for the time that Dalton was doing this. So all matter is composed of atoms. I'm going to say indestructible atoms. We'll learn later in this course that atoms are actually not indestructible. Atoms of a same element are identical. Also, we'll learn today this is not true. Atoms combine together to form simple whole number ratios. His idea about this was also not correct. But we're still going to go by this idea that we're going to get whole number ratios. But his was even more simplified than we'll see. We won't get into what he thought, but we will always see these whole number ratios. And this part's true. As long as it's a chemical reaction and not like a nuclear reaction, the atoms are not created or destroyed. So you have these set of rules. Most of them are not 100% true, but pretty close to being true. And for this point in time, that's pretty good. So then we're going to fast forward like another 100 years or so. And we're going to see what is the atom made of. So the first subatomic particle that we find is the electron, and that's by J.J. Thomson. This is really from like 1880 to 1920, where this is where we are. So J.J. Thomson finds the electron. And then after that, we have... I won't get into how he found the electron. It's interesting, but I'm going to spend my time on talking about the next experiment. So another English scientist who is, well, actually he's from New Zealand, but he worked in England, Ernest Rutherford, discovers the nucleus. This is the gold foil experiment. Okay. The idea is we didn't know what the atom will look like. J.J. Thomson, he took a stab at like a hypothesis of what the atom would look like, and he came up with the plum pudding model. So a plum pudding is basically a muffin with little bits of plums in it. And so he thought it was, the atom was going to be something like this, where we have positive charges, he must have thought it was negative charges because he's finding electrons. We'll make the plums little negative charges. And then it's in this scoop, which is all the positive charges. So something like that. Everything's just mixed together. He knows they can't have a bunch of negative charges together, so there's positive there as well. And this is our plum pudding, which is not the structure. The only reason why we mention this is to compare it against what the structure is. So what Rutherford then did was this experiment that showed that this hypothesis was incorrect, and he proposed, from his observation, a different hypothesis, which in its own way is also incorrect. So the gold foil experiment is, first let me show you what the his idea of what the atom is, and then how this fits the gold foil experiment, and how the plum pudding wouldn't. So there are basically a bunch of little positive charges all stuck in the middle of the atom. And what J.J. Thomson found, the electron, is going around the outside. Something like that. Like a planet circling around the sun. That's a planetary model, and that's what Rutherford proposed. So then finally, so what is the gold foil experiment and how does it all work together? So he is going to take, Rutherford is going to take a positive charge with high energy. These are alpha particles. And he's going to shoot them at gold foil. And we know that the gold foil is made up of nuclei and atoms. So there's all these atoms together in this gold foil. It's very thin, so you can almost think of it being like on the atomic level thin. It's very, very thin. There's not many atoms stuck together. And what happens is that as these atoms go through, most of the time, they are going to find these gaps. And my positive charge is going to go straight through, and it's not going to get deflected. So on the back side of the experiment of this gold foil, is film. The film will tell us what collides. So most of the time, the things go straight through, the particles go straight through, they hit these gaps, and they go to the backside. So we see a lot of marks over here of the positive charges just going straight through. Now, once in a while, the particles get very close to the positively charged nuclei, and positives repel each other. So what happens is they come out at these wide angles. So these wide angles, then, we'll see them, but we won't see them as often because the two particles are so small that statistically they're not going to run into each other all that often. Finally, Rutherford decided to check very, very large angles, like all the way out here. And what he saw was they would run into the nuclei and make a U-turn. So even less frequently, like just very, very rarely, but it happened, he would see these extremely wide angles. And why is that happening? This is just a dead-on hit onto an atom. It doesn't happen very often because these particles are small and the gold nuclei are small. So it's unlikely that they would going to run into each other, but it does happen. So this wouldn't make sense, or these results wouldn't make sense with the plum pudding model, because in the plum pudding model, there is no like small center of the nucleus that's positive. It's just distributed. So the alpha particles should always be running into positive charges. So based off this observation of these wide angles, what Rutherford came up with was the planetary model, saying that there's a very small, highly charged positive center of the atom, which was the nucleus, and it's surrounded by these negative charges. So we have the planetary model, highly charged positive center of the atom, surrounded by negative charges. And the part of it that's wrong, that Rutherford didn't get right, is that he thought that the negative charges would circle around the nucleus, but that's wrong. We'll talk about what is correct in the next lecture. The part about a very small nucleus is fine, is correct. This is the nucleus. Those positive charges, by the way, are called protons. The negative charges are the electrons. So the rest of what we classify as the volume that an atom makes up is just the space that the electrons move in. So continuing on in historical, so Rutherford discovered the nucleus and the positive charges that are in the nucleus, which is the protons. That's not right. Finally, we have the last scientist. We won't go into what he did, but he worked with Rutherford. He did this in Rutherford's lab. So Rutherford gets a lot of credit for this as well. The neutron was found. The neutron is also a particle that is in the nucleus. So the atomic particles, once again, are protons, neutrons, and electrons. So we have the proton, the neutron, and the electron. The charge of the proton is positively charged, it's +1. The charge of the neutron is 0, it's an uncharged. The charge of the electron is -1. The mass of a proton is 1.007. We're going to use this unit of atomic mass units, which is U. Which we'll talk about how it relates to the kilogram later. The most important part of this is not what the actual numbers are, it's just the ratio. You can see that these two are almost identical. It isn't true that the neutron is a little bit heavier than the proton, and the mass of the electron is insignificant in comparison to the proton and neutron. And then once again, the locations, the proton and the neutron are found in the nucleus. They would comprise the nucleus. And the The electrons would mix up the space of the atom, or the volume of the atom. So we need to describe all the elements that we know, and what describes them is the number of protons. The number of protons of an element is called its atomic number. So we can mess around with the number of neutrons or electrons, but not change the identity of an element as long as the number of protons is constant. The symbol for protons we use is capital Z. And then we can also call this the atomic number. An atomic number just means number of protons. So we can look at this periodic table here, and on this periodic table, these numbers that appear above the elements, these are the atomic numbers. So there are 2 protons in a helium nucleus. Anything that has 2 protons must be helium. There is no helium that has 2, and nothing that has 2 is not helium. And if you go through this periodic table, you'll see nothing shares the same number of protons. I'm going to come back to this periodic table a bunch of times. So we mentioned some stuff already about elements. We said that the symbols either have just one capital letter or 2 letters. And then the names either are, they're named after either things we've just known for a long time, and so we just have names from antiquity, or for newer elements that have been found more recently, or even some of the elements have been synthesized. Those are usually named after places or people. We've just always called it something, and so that's what we just continue to call it. Other things, we have it from Latin names. For example, sodium. It has a symbol of Na based off its Latin name, which is natrium. And then another example of this is potassium. And this is capital K, and this is from its Latin name, kalium. And so here is K, is kalium. It was actually from the Arabic, for the Arabic word of ashes, which they then Latinized. So it's Neo-Latin. And there's other ones that are named after places and people, like ES is named after Einstein. This is Einsteinium. And BK is named after UC Berkeley. It's Berkeleyum. So is CF for Californium. So the periodic table itself, it came around in the mid to late 1800s, and it was first organized this way by Mendeleev, a Russian scientist. And basically, he just listed out the elements in increasing atomic mass. So this was done by mass, where it would heavier and heavier and heavier elements. And so then he would have spaces, like he had a space here where he knew there should be an element because he had this mass. Then they knew about gallium and they knew about arsenic, but they didn't know about germanium. So then, but based off its mass, he was able to figure out that there should be an element there. So he listed them this way by increasing mass, and he listed columns this way by similar reactivity. And as I said, based off that, he felt like there should be a missing element. So he had these spaces of where, based off of what he's observed, he should have elements. And in a lot of those cases, we found things. And we'll talk about reactivity as we go through this class as well. So he noticed missing elements, and he proposed that these elements should exist, and we did find these things, and even more than he thought were missing. Okay, so let's go now talk about the actual periodic table. This is the IUPAC, or the International System of Numbering the Columns, and this is what we'll use. So the columns are called groups or families. I'll more likely use group. The row is called a period. So the row is organized by increasing mass or increasing atomic number. For the most part, the mass increases as well, but if you look through this, you will see some cases where the mass doesn't increase. The mass, by the way, is the second number down here. This is just how many protons there are. And the columns are by similar reactivity. As I said, we'll talk about what that reactivity will be in a little bit. And I get a little bit into what Mendeleev knew about the elements. The other thing that we're going to organize them by are the types of elements. So the types of elements we're going to say that there are metals, nonmetals, and semimetals. We'll talk about what their properties are after we find out where they are in the periodic table. But this side of the periodic table, the left-hand side of the periodic table, is where the metals are. So all these ones would be metals, 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 metals. The semimetals are just a set of elements that have metal-like properties, but they also have some non-metal-like properties. So there's just a set of them that you have to know. B, S, I, G, E, A, S. Antimony and tellurium. But really, it's these four that we'll see most often in this class. Tin is a metal. And then the other ones are nonmetals. Oops, I made a mistake. There is an example. There is a nonmetal on the left-hand side of the periodic table. It's hydrogen. So hydrogen's a nonmetal. So is helium. So are all these elements here. So are these elements. So are these elements. And then these last ones are hard to say what they are, but they're most likely nonmetals. So those are the nonmetals. So what are the properties of the metals and nonmetals? They're conductors. This is both of electricity and heat. They are malleable, which means you can bend them. They're ductile, which means you can stretch them out and form wires. This gets into the chemical reactivity, but they tend to lose electrons. And then examples are, there's plenty of examples, iron, copper, zinc, magnesium, sodium, all these are examples of metal. They look shiny. They look like metal. Nonmetals they're pretty much the opposite of all these things. They are insulators. So they're poor conductors of electricity and heat. They're brittle. So if you try to bend them or stretch them out, they just crack and fall apart. They tend to gain electrons. And they're not shiny, they tend to be dull. And then semi-metals are kind of the in between. They have some kind of properties that are like metals, some properties are like non-metals. For example, there are semiconductors. They're not great at conducting electricity, but they can do it under some circumstances. So now, continuing talking about the periodic table, we can classify important families or groups. So you should know these names of these groups. So we'll know about one, which is the alkali metals. I'm going to write this down in the next slide. This one, which is the alkaline earth metals. You should know this group here as the transition metals. So it's going to go 3 to 12. And then you should know the name of this one, which is going to be the halogens, and this one here, which is going to be the noble gases. Actually, I can just write it here. And I'm just giving you a little bit of information about another thing. Actually, the other thing that we can say is another grouping is that the main group elements which we will mostly talk about in this class, the main group elements are 1, 2, and then 13 through 18. So this is the main group, and this is the main group. So I said that the periodic table is organized by similar properties. So everything in this group has a similar property in that it's reactive with water. So they could take some sodium, add water to it, and you would see kind of a vigorous reaction. The other thing is that they like to form a 2-to-1 ratio with oxygen. And this is the part of it that Mendeleev would have known what the ratios are in the elements. So you know that water is H2O. It's right here. But when lithium forms a compound with oxygen, it's also Li2O. So Mendeleev just listed everything that formed 2-to-1 with oxygen in that column. In the alkaline earth metals, these ones are less reactive, but they form a 1-to-1 ratio with oxygen. So if we see, say, calcium forms with oxygen, it would form CaO. And then something about the halogens. The halogens are very reactive. Fluorine is an extremely reactive element. And then it's right next door to this group. The property of these groups is that they're inert. Inert means they are unreactive. So helium, neon, argon, krypton, they took a long time to find these ones. These ones weren't found until the 1900s because they are unreactive. A lot of the way that we knew these elements existed is by their reactivity. So because we couldn't see them do any kind of chemical reactions, we just didn't know that they were there. And that's kind of similar to these ones, but the opposite. These ones are so reactive that you can't see them in their elemental state because they're always going to be reacted away. So these ones also took a while to find. I said I would mention this. I'll do this now. There are 7 diatomic elements. So di means 2, atomic means there's 2 atoms. An element is made up of the same type of element. So at room pressure and room temperature, here on Earth, these are the elements that exist as a diatomic. So hydrogen, which has the symbol H all by itself, its diatomic is H2, but that's how it exists. So whenever I say hydrogen, I'm talking about H2. Nitrogen, and I'll point these out on the periodic table once I'm done listing them out. A mnemonic is never have fear of ice cold beer. N is the nitrogen, H is hydrogen, F is fluorine, oxygen, iodine, chlorine, and bromine. The way that I was taught to remember it is that there's 7 of them. And if you go from nitrogen to oxygen to fluorine to chlorine to bromine to iodine, it looks like it makes a 7. Plus there's hydrogen. So there's 7 of them. They're all pretty much grouped close together, plus hydrogen. So you're responsible for having those, for memorizing those. So the charge of an atom is related to its protons and electrons. So charge would be equal to protons. How many protons are there in a certain atom minus electrons? So an ion is when you have unequal numbers so that you get a charge. So an ion is a charged particle. The particle that we care about are atoms, or even molecules, but we'll get to that later. So the protons do not equal electrons. There's 2 different names of these. Cations, these are positive charged. So you have more protons than electrons. And then the other term is anions. Which is just the other way around. We have more electrons than protons. So we can look at the periodic table and we can predict the most stable charges things will make, at least for some atoms. The other ones we'll learn about how that works later in this class. And in the next lecture, we'll learn why this happens the way it does. But for right now, we just have to know what these numbers are. So we said that the metals like to gain electrons. These ones, we said the metals like to lose electrons. These like to lose 1 electron. So they become positive 1 when they form an ion. So if they're an ion, which is one way they can exist, this is the way they'll exist. They don't always form ions. These ones become positive 2. These ones we'll talk about later. And then the ones that are metals, aluminum, gallium, and indium, they like to become positive 3. So the aluminum that you're familiar with, aluminum foil, it's not the ion form of it. It's the metallic form of it, so it does not carry a positive charge. But if you have a compound that has, where it is charged, aluminum will be positive 3. So the other ones we're going to know in this column, just nitrogen, it forms negative 3. Oxygen, sulfur, and selenium, they like to be negative 2. And then fluorine, chlorine, bromine, and iodine, we'll say they're negative 1. These later ones, they have some metallic properties, and so they can form positive charges. Acetine is extremely reactive. And then these ones we just don't know that much about. And I said that the noble gases are inert, and so they really don't get ionized, so they pretty much always stay 0 charge. So a good example is sodium. You've probably never seen metallic sodium, but it just looks like a piece of metal. In sodium chloride, table salt, which you've seen before, it has sodium ion in it. Does not look metallic. So even though both of them have sodium in them, this is just metal sodium all by itself. And this one has sodium in as well, but it's in the ion form. It looks different. So group 1 metals, hydrogen, which is, even though it's a nonmetal, it's included in this group because it also likes to become +1. So that's its reactivity. Group 2 metals, become +2. And then we're not going to talk about the transition metals right now, so we'll go all the way to group 13. This is +3, and these ones are only going to include aluminum, which is what we'll talk mostly about, but also gallium and indium. Nonmetals, it's the same thing. They can be ionized as well. It's the same kind of thing that, depending on if it's the neutral form or the ion form, they'll look different. So chlorine is a gas. It's green. Chloride, which is the other part of sodium chloride, in table salt, does not look like a green gas. It looks much different. So the chemical and physical properties of things would be different depending on if the element is ionized or not, but it's still made up of the same thing with the same number of protons. And what we saw was group 15, so just the nitrogen, becomes -3. Group 16, really what we're going to work with there is oxygen, becomes -2. I'll go over the nomenclature for the charges as well. And then group 17 becomes -1. And this is all the halogens. And then finally, I won't write it down, but group 18 is inert. It does not ionize. So we have the symbol. And then up here, this is where we write the charge. If the charge is 0, we write nothing. Okay, so then the next thing we're going to talk about is what's going on in the nucleus. So the number of protons that a particular element has to be the same. But the number of neutrons from one atom to another, it can be different. But it would still be classified as the same type of element. For example, you could have carbon that has 6 neutrons, 7 neutrons, or 8 neutrons, but they all must have 6 protons. So we want to be able to label what type of isotope we're talking about. So what an isotope is the relationship between elements of the identical elements with different number of protons. Same element. Different neutrons, sorry. Okay, so here's the symbol. We're going to write the atomic symbol. In the upper left-hand corner, we're going to write what the mass number is, which I have to define. And then down here, we'd write the atomic number. The atomic number is going to be optional. You don't have to write the atomic number because the symbol itself will tell you how many protons there are as long as you consult the periodic table. All right. We said that there were these 3 different forms of isotopes of carbon, so we can write their atomic symbol. So this is going to be the symbol. This is how many protons there are. This is how many neutrons there are. And then this is going to be its mass number. Protons is also its atomic number. To be carbon, you have to have 6 protons. In this case, this only has 6 neutrons because 6 plus 6 is equal to 12. This has 1 more because 6 plus 7 is equal to 13. And then finally, this one has 8 because 6 plus 8 is equal to 14. So the mass number is just the sum. That's what we're writing in the upper left-hand corner. That is going to be 12, 13, and 14. Not all isotopes are stable. So radioactive isotopes, if given on long enough time, depending on what they are, they'll decay away and turn into something else. So on the periodic table, it gives us information about the stable isotopes. Some isotopes there are no stable versions of it, and then we just give the mass number of the most stable isotope. And I'll show you that on the periodic table. So these numbers here, this relates to the masses of the stable isotopes on average. For some elements, none of them, there are no stable isotopes that exist, and so we just give the mass number of the most stable isotope. So you can see technetium in parentheses, it says 98. So there's no stable isotope. everything having to do with technetium is radioactive. So we just give the most stable isotope. And then you can see a lot of elements that have no stable isotopes. All of these ones have no stable isotopes. These ones, some of them do, some of them don't. No stable isotopes. Okay, so now we need to talk about natural abundance. This was discovered by J.J. Thomson. So natural abundance deals with the distribution of the isotopes that exist for a particular element. So what J.J. Thomson did this first, he found out about neon. So there's three stable isotopes. Of neon. There is neon 20. There is neon 21 and neon 22. If you went and just collected some neon naturally occurring on Earth, what you'd find is that 95% of it is neon 20. A very small chunk of it is neon 21, and the balance is neon 22. These numbers are the abundances of that element. Some elements only have one stable isotope. Other ones can have like 10 different stable isotopes. It really just depends on the element and how stable that nucleus is. So only thing I'll ask you to do is just to work with these numbers. So the last thing we're going to talk about is how do we get these numbers? So we know that this is based off of the stable isotopes, but how? Before I get to that, I'm just going to talk about what a weighted average is. So imagine we have an exam and 75% of the students get a 90% on it, and the rest of it, 25% of the students, get a 80%. I'm just going to write it. It's a 90. We know that the average is going to be somewhere between 90 and 80. But it's not just 90 plus 80, because 75% of the students got a 90 and only 25% got an 80. So we would think that the average should be closer to 90 than it would be to 80. The way that we find this is we take our percentage, percentage times score for all the scores. And then we divide it by 100. And that dividing by 100 just gets rid of the sum of the percentage times score for all the scores divided by 100, and that gives us the value. We divide by 100 to get rid of the percentage. So for this example, what was the average score? It would be 75% times 90 plus 25% times 80 divided by 100. And I'm just going to find the answer. And it gives me 87.5. We're going to do the same thing with our elements. So let's go back to neon. Neon was, we had neon 22. We had neon 20. 1. And we had neon 20. And we knew what its percent relative abundances were. So these are the percentages that are due to, I did it backwards. The percentages that were due to those mass numbers. So then the last bit of it that we have to work in is we need a mass. So in the exams, we had scores, and here we have masses. The mass is not exactly going to be the mass number, but it's going to be something pretty close to it. So as an approximation, we'll say that the mass is 20. And the units of mass, we said earlier, there are these units of U, atomic mass units. They could be 21, or it could be 22. So then how do we find how heavy is neon on average? We just do the formula, which would be 20, which is my mass. I said I'm going to do percentage first. So it would be 90.5 times 20 plus 21 times 0.27 times 21 plus 9.25 times 22 divided by 100. Just give me a minute to do this calculation. and then we're going to compare it to what it says on the periodic table. If there's a difference, it's because we're using approximated values here. How you get closer values, you can look them up, but you're not going to be responsible for that. And that gives me 20.19. I'm going to say 20.2. So if we go back and look at the periodic table, you can see we came up with 20.19 using our approximate values, and the actual average is 20.18. Why is it a little bit heavier than 20? Because there are some elements that are in that average that are a little bit heavier. The other thing, and this is not going to actually work in every single case, but most of the time, here's clarifying, this is not always true. The mass number of the element with the highest abundance is the average mass rounded to the closest whole number. So let's just go through some examples and we'll see that that's true. So what would we say the most stable isotope of neon is? Well, we would look at the mass of neon, which is 20.18. So you would guess that the most stable isotope of neon is neon 20. If you looked at carbon, you would look at this and say, based off this number here, it looks like most of the time it's carbon 12, and that's true. The most stable isotope of carbon would be carbon 12. And it works for a lot of the cases. A case that it wouldn't work is bromine. You're not responsible for knowing this, but if you looked at this and said, oh, that's really close to bromine 80, and so we would say like, oh, I think bromine 80 is the most common isotope. In that case, you'd be wrong. It's a 50-50 mixture of bromine 79 and bromine 81. So if I ask you to do this analysis, if I give you a like a multiple choice question and say, what's the most stable isotope of helium? You can make that approximation. You could say that the most stable isotope of helium is going to be helium-4 because it's closest to this. I'm not going to ask you cases where it's not true. There is the quiz that I posted. I am working on a worksheet which I'll post, And there's also the homework that is posted on chapter 4, but then it also has chapter 9, which we will get to on Thursday.